Okay, so in this video we're going to take a look at Gauss's law, and we're going to use it to determine the electric field in between two parallel sheets. And two charged parallel sheets basically forms a parallel plate capacitor. And we're going to have uniform charge density across the two surfaces. Now, something that you may not remember or may not have picked up in your reading, but outside of an ideal capacitor, the electric field is going to be zero. So before we get started with the actual use of Gauss's law on this situation, I would like for you to, in light of our last video, take a guess at what you think the final answer is going to be whenever it comes to the electric field inside a parallel plate capacitor. What you should have said is that it's twice as large. The field is twice as large. And that should be logical to you. When we have an infinite sheet, we only have one surface which is creating an electric field. So, we have one sheet like this, an infinitely long sheet, and the electric field from that is going to be this. But if I were to place another sheet above it, which is opposite in charge, it's going to add an electric field to that. Okay, so this could be the positive sheet, this is going to be the negative sheet, and we end up with the field doubling. So that means our final answer should come out to be E is equal to sigma over epsilon naught, and that comes from doubling the single sheet equation, which was sigma over 2 epsilon naught, which you might see as 1/2 sigma over epsilon naught. So if we have two of these, it's just going to become sigma over epsilon naught. All right, now let's get back to our particular situation with this application of Gauss's law. So the first thing we need to do is just draw a picture of what's going on, and I'm going to do that, and we're going to come back to it. Okay, so what I've drawn here is just one plate of a parallel plate capacitor, and our Gaussian surface is going to be tucked inside of the metal plate itself, one of our surfaces. We don't want to make our Gaussian cylinder pass all the way through, and in fact what I've drawn right here, that's just meant to give you an opening that you can see inside, that my Gaussian cylinder is just going to poke part way into the metal sheet. You don't want to poke it all the way through the other side though. If you do, you should still end up with the same result, because the electric field outside of the capacitor ideally is going to be zero. But we can say very definitely that the electric field inside of the metal sheet is also going to be zero. There is zero electric field in there because it's a conductor in electrostatic equilibrium. The Gaussian surface is going to poke into this conductor, and we have another conductor on the other side, but we're not going to put the Gaussian cylinder into that other conductor. It's going to terminate somewhere. It's going to terminate somewhere in between the two plates. Okay, so our Gaussian cylinder is going to be in here. Now the reason for that is our electric field is coming this way, and we already know that the area down here, I'll call this A1, we already know that in A1 the electric field is equal to 0. And this A2, the area for the end cap here, that needs to be non-zero, because if we look at the area for the wrapper, the area here I'll call A3, what we find is that the electric field there is going to be 0. Okay, so we can't have everything going to 0, otherwise this is never going to work. So you might want to think of it as the distance r from the surface to where we are trying to find the electric field in between the two plates. So we're not trying to find the electric field at either surface, we're just trying to find the electric field in between the two plates. We start with Gauss's law. The integral of E dot dA is equal to Q enclosed over epsilon naught. And we have three surfaces of our cylinder to consider. And anytime you use the cylinder, you have to consider three surfaces. So we end up with the flux of this surface, A1, is 0 because the electric field is 0. The flux of this surface, A3, is going to be 0 because the cosine of the angle is 0. All right. In other words, the field is parallel to the area instead of perpendicular. So the only area we have to worry about is A2 because the field is coming perpendicularly through A2. So we end up with E times A2 is equal to Q enclosed over epsilon naught. And to get Q enclosed, we're going to use Q is equal to sigma times the area, or sigma times pi r squared. The area of, now that area that we're referring to for sigma, that's going to be this area right here. Okay, that's at the surface. The area A2 is a circle of the exact same dimension, so we end up with E times pi r squared is equal to sigma times pi r squared over epsilon naught. Now I should be using little r here, or I'm sorry, capital R, because that's a different r, because the wrapper is what would give us the distance from the surface to the point we're interested in. So I defined that as little r, and so the area is going to be capital R for A2. Okay, so we'll say that that's pi r squared. Nonetheless, what we find is that the two areas cancel out because they are the exact same dimension, and we end up with E is equal to sigma over epsilon naught, which is exactly the answer that we were expecting. Remember, this comes from, here's our one parallel plate, we'll say that's the positive plate, here's our negative plate, and the electric field due to the positive plate we know is going to be this. The electric field due to the negative plate is going to double that, and so the total electric field is going to be that.